Hello and welcome to Lecture 5 of the Computational Physics course, Physics 352, and I'm back, your instructor, Sasha Chikavskoy. Let me start with a few reminders. Assignment 1 was due on Tuesday, January the 26th, and if you haven't yet submitted it, please do so, unless you have obtained an extension from me. Assignment 2 is on Canvas now, and it is due a week from Tuesday, on Tuesday, February 2nd, a minute before midnight. And finally, assignment 3 is coming to Canvas very soon. One really cool problem, part of the assignment 1, was the stack smashing example. And here is an example of stack smashing, just for us to understand what's happening there better. So what we did, we introduced two string variables, hello and there. These are just arrays that contain strings in them. We then loop over the element 6 and further down the road, where we stop at the 6th element. Here it turns out that on my machine I only need to overwrite one single element of the array in order to create something interesting. So what I did is I set b of 6 equal to j. So what that means is that the 6th element of b would be, let's count that, 1, 2, 3, 4, 5, 6. But the counting in C starts from 0, so actual proper way of counting is 0, 1, 2, 3, 4, 5. So 5 would be the 0 terminating character, and 6 would be the one byte that immediately follows the 0 terminating character of the there string. And somehow, once we go through this and print out the result, we're going to find that hello got replaced with jello. What's going on here? Well, the answer lies in here, in the addresses of the B and the A arrays. And here what I've done is I've printed the addresses of the B array elements and the addresses of the A array elements, and I'm printing out all of them from the 0 element to the 5th element. And you can see that the addresses are sequential, which means that although we have declared the array A first, in memory it comes in last. A comes after B, although we declared B after A. And then, of course, if we overwrite the element B of 6, right? B of 6 would be right here. It will be the same as A of 0. That's why the 0th character of the A array got replaced with J. And that's how we got from hello to jello. So how did we get jello? Well, of course it seems counterintuitive that we declared A before B, but that's because static memory allocation is done on the thing called stack. And stack, typically, there are exceptions, in some cases, grows downwards from high addresses. So what is happening in my machine might be not representing what happens on your machine, is that because for some of you, you actually needed to step outside of the B array by a few bytes in order to traverse the gap between the A array and between the B array and the A array in memory. In my case, in my machine, this gap didn't exist. So the A array started immediately where the B array ended. But on some machines, you had to take a few steps further to get from the end of the B array to the beginning of the A array. And to reiterate, stack grows downwards. So you can see that these are high addresses, These are the low addresses. And the stack, which is the everything that you declare at the beginning of main, will go down as you add more and more declarations. So if you declare A first, it will be sitting high up in the addresses, and then it will place things that were declared later at smaller addresses. That's precisely why A is sitting after B at higher addresses. The reason for why there is a gap sometimes is because compiler sometimes pads the allocated memory. So for instance, it can pad the A array with memory that is not used by you, the user. And that's why there could be gaps between the A arrays and the B arrays. Notice that sometimes the operating system can catch the memory access that we're not supposed to be doing, like in this example, and show an error message. I've shown an example of that in the previous lecture. Notice that there is this other interesting part of this diagram that shows heap, and the heap grows in the normal increasing direction. And eventually the two try to converge once the full memory is exhausted. We're going to be talking about heap later, and in fact you're going to be dealing with heap in homework 2, which is now online. So what is a way for you to try and protect yourself from out of bounds memory access? One way to do so is to enable the memory leak catcher using functionality that's built into the GNU C compiler or the GCC. For that, you add a combination of these two flags, -f sanitize address and -f no emit frame pointer. And then you continue the compilation as usual, except perhaps you might want to add -g, which keeps the symbols, that is the names of variables and the names of the functions, in as part of the executable, so that these two switches can give you some useful information about where the out-of-bounds memory access has occurred. For instance, here it tells you that the address sanitizer detected stack buffer overflow at this address that it gives. And moreover, it is telling you which line this out-of-bounds access occurred, and then it is telling you which variable and which line it was defined as well. Moreover, it then gives you the details of the memory dump, where the memory in question is located and where the special padding is used in order to catch these sorts of writes. So the way the memory leak detection works here is the GCC compiler provides padding to all of the allocated memory, and if it detects access or modification of these allocated memory, then it issues a complaint. So this describes what exactly is happening here, and you can look at the implementation of this at this link. Not all of the memory access is caught, only some of it, so this is by no means a foolproof solution, but it can be extremely useful if you're trying to weed out a memory access bug that is typically very hard to catch. Notice that GCC now has other functionality that can catch the stack smashing, and you can try and use that. Please take a look at the previous lecture. So what are we going to be talking today? We're going to warm up in computational physics. We are slowly moving away from learning how to code things up to what are we going to code, what sort of physics are we going to be studying. And we're going to start with the discussion of radioactive decay and the numerical methods for solving ordinary differential equations, or ODEs for short. We're going to be looking at various numerical methods for solving the ODEs, such as the Euler method and others, such as Rangikatta methods. And finally, the text in our book that I would like to cover today, coming from chapter 1 and also from appendix A. So what is radioactive decay? There are several types of it, and there are different decay products that characterize these different types. For different forces, you can get alpha and gamma decay and beta decay. And for instance, alpha and gamma, they are mediated by electrostatic and strong nuclear forces, whereas the beta decay is a manifestation of the weak force. I'm not going to be going into the details of this physics, but what we need to know here is that elements that contain more than 82 protons, they have no stable isotopes. So for instance, a uranium-235 contains 92 protons and 146 neutrons. So everything to the right of this line of 82 protons, so this is the number of protons on the x-axis and the number of neutrons on the y-axis, all of these elements to the right, they have no stable isotopes. You can see this in color, where the color here shows the different types of decay. For instance, the black color shows that this is a stable nucleus, and various colors show the different types of decay. So you can see that there is this island of stability, but it doesn't extend beyond 82 protons. So all of the nuclei to the right of this line are unstable. So what is the physical reason for this instability of heavy nuclei? And this comes from the basic energy conservations. If we plot the average binding energy per nucleon in mega electron volts, all on the y-axis, which goes from 0 to 9 mega electron volts per nucleon, versus the number of nucleons in the nucleus, which ranges from 0 to around 240, you can see that the specific binding energy per nucleon is going down with the increasing number of nucleons. So that means that if we have a lot of nucleons, it actually is energetically more advantageous for the nucleus to split into two pieces, each of which is smaller than the original nucleus and therefore has a larger specific binding energy. So, of course, the ball tries to roll down off the hill into the valley, and that is precisely what the nucleus tries to do. It tries to assume the lowest energy state. It is energetically more favorable to split into lighter daughters, and the physics that causes that is the electrostatic repulsion, which dominates these high nucleon number nuclei. So what happens once this decay proceeds? The number of the radioactive nuclei keeps going down in time, and the rate of decay, or the rate of change of the radioactive nuclei, the number of radioactive nuclei versus time, dn dt, is given by the current number of radioactive nuclei divided by a characteristic time scale, which is the lifetime of the nucleus. And the inverse of the lifetime, lambda, is the decay rate. So you can find the solution to this simple ordinary differential equation in the following form. The number of remaining radioactive nuclei at the time t is equal to the initial number at time equals 0 times the exponent e to the power of minus t over tau. So then we can use this equation to any process that is characterized with a probability of change that is proportional to the instantaneous value. For instance, a capacitor discharge, heat transfer, and so on. So how do we solve these types of ordinary differential equations, or ODEs, numerically? Well, we rely on the Taylor expansion. So we say that n at time equal to t is equal to n at the initial time plus the first derivative times delta t plus the second derivative, actually this should be 1/2 over here, times delta t squared, and so on and so forth, higher order terms in the Taylor expansion. So what we do in the simplest method of solving the ODEs numerically is we stop this expansion at the first order. So n at t plus delta t will be equal to n of t, right, times 1 minus delta t times lambda. Remember, when we wrote down the analytical solution for that, we can expand the exponential in the Taylor series, and that is what it comes out to be. So the truncation error, or the error that we're making compared to the analytic solution, is of course proportional to the next order term in the expansion, or delta t squared. Once we reach the final solution though, we're going to have to go through a few steps. So we will have to multiply this error. So we will have to add all the errors at every time step. And the number of time steps is inversely proportional to delta t. So once we add up all of those errors, the error will eventually be proportional to delta t to the first power. So whereas the local truncation error at every step is the second order error in the time step, the global truncation error is of the first order in the time step. So there are methods that are better than that. There are methods that are high order in the time step, and that's good because the higher the order of the scheme, the larger is the power, delta t to power 2, 4, or even higher. And because delta t is small, when you take it to a high power, it means that the error will go down. Another way of thinking about it is if you decrease delta t by a factor of 2, the error is going to go down by a factor of 2 to the power at which the scheme, to the power of the order at which the scheme converges. So in the case of this first order scheme, the error will go down by a factor of 2 if you decrease the time step by a factor of 2. But if you had a high order scheme, let's say second order scheme, it would go down by a factor of 4. So a little bit of investment into resolution in time can bring down the error by quite a bit with high order schemes, and Rangikatta methods are an example of such high order schemes. So the simplest way of solving this problem, like we looked at on the previous slide, is the Euler method. So we're going to say that the value of our solution at the new time is ti plus 1 is equal to the value of our solution at the previous time, ti plus some function that is giving us the decay rate evaluated at the previous time times delta t. So what we've done, we have expanded this problem in the Taylor series. Again, the factor of 1/2 is missing over here. Apologize for that. And we have dropped the higher order terms in order to arrive at the Euler method. So what is going on here graphically is if we plot y versus time, then we see that the true solution is a curved trajectory, whereas our Euler method is going to go parallel to the tangent of this solution. So when we take a time step of delta t forward, in this case, we're actually going to deviate from the true solution by this amount. So the Euler method cannot account for the curvature of the solution. And the error here is going to be, in one time step, is second order, controlled by the degree of curvature. We could try and improve on that. In fact, we could even get an exact solution, so we would hit precisely in the bullseye if we were to step not with the derivative evaluated at the point itself, but evaluated at the point in the future. So if we were to take this slope from the future and start out at this point, t0, and take a step forward, we could hit the exact right answer. So that is what the Rangikatta methods are all about. These are iterative approaches that try to zero in on the right solution, taking into account higher and higher degrees of curvature of the solution. So this is what Rangikatta methods do. Let us start with looking at the simplest Rangikatta method, the second order Rangikatta method. Here, in a nutshell, instead of going immediately from the initial time to the final time of the time step, we're going to go halfway, evaluate the derivative, and then use that to go all the way. So this is what we're doing. The new time will be the original time plus 1/2 of the time step, right, going halfway. Then we're going to figure out what is the value of our variable when we go halfway. So we evaluate the derivative at the initial state, and then multiplied by half delta t. That is going to be our value at half time step. And then we're going to evaluate the derivative at this half time step value at the midpoint. And starting with the original initial point, we're going to go all the way. So t prime is the midpoint of the interval, and x prime is the Euler approximation of our solution at this midpoint. The computational cost, of course, of this method is higher by exactly a factor of 2, because now instead of taking one Euler step, we take in basically 2 Euler steps, but with this new way of computing the derivative. However, the local truncation error and the global truncation error are higher order, and they go as delta t to the third power and delta t to the second power. So our method is globally second order method. The error scales as the second order in the time step. And that is awesome. So let us visually represent what this Rangikatta method does. So this is the beginning of the time step, this is the end of the time step, and this is the true solution here shown with the blue line. So first we take the Euler step forward by half the time step. So we're going over here, evaluating the derivative over here at the midpoint, and then we're going to remember this derivative, come back to the original point, and we're going to take the Euler step forward now, going all the way, but with this new value of the derivative that was evaluated at the midpoint. So this way we're trying to account for the curvature of the solution, and that is what improves the answer. Of course, the final answer is still not going to be exactly correct, because there could be other high order corrections to this. It's not going to be exactly a parabola. For a parabola, this method would have given an exact answer. So for Rangikatta of a higher fourth order, we need to take 4 Euler-like steps. So let us take a look at this diagram where all of these steps are enumerated. So we're going to start with the regular Euler step, starting at the initial time. So the t1 prime and x1 prime are at the initial point. And what we're going to do is we're going to step forward by half a step, evaluate the derivative, So we're going to step forward by half a step, and then we're going to evaluate the derivative over here at this point, at the midpoint. We're going to then go by half a step, starting with the initial condition. So we're going to take this slope, and starting with the initial condition, we're going to go by half a step again, evaluate a new slope over here, and then we're going to go again starting with the initial condition with the slope, but this time by a full step. So we're going to go from here, from the initial condition, all the way out to the end of the time step. But this is not the full answer yet. The full answer that gives you the highest order approximation comes about by taking this combination of all of the different answers between the steps. So it's going to be 1/6 times the sum of all of these different values of f with the weights that add up to 6, right? 1 plus 2 plus 2 plus 1, that will be 6. So this is how we add up these steps such that the errors of each of these steps magically cancel out to the maximum, the highest order of accuracy possible. So we can use different types of time stepping for solving ordinary differential equations, and we're going to explore the effect that the different types of integrators have on the quality of the solution. By no means these are the only types of integrators that are available. There are more advanced integrators and much more advanced techniques that can be much better performing in specific situations. But for now, let us try and focus on applying the simplest of these methods to the radioactive decay problem. And we're going to start with the decay.c. This is the radioactive decay code that's given in section 1.3 of the computational physics book. And because everything is mirrored, you can see that this book is also mirrored, so you can't actually read it, but the picture is familiar. So this is the book, the second edition by Giordano and Nakanishi. So this is a clean function main that compartmentalizes the various steps in our solution. At first, we're going to initialize our integrator, then we're going to calculate the solution, and we're going to store it. However, this method hard codes the use of the Euler integrator. It also uses global arrays, and it's not great from these points of view. So why don't we try to make a more general, a reusable Euler method? And for instance, we can get started by writing a single Euler step that will take the value of the variable at the current time, the value of the right-hand side of the equation, f, the derivative, and the time step itself, delta t. And it will return the answer at the end of the Euler step, where we take x and add the derivative times delta t. So that is one very simple Euler step. So what are we going to do in order to call this function? In the function calculate, this function is called in the following way. In a loop from 0 to the max number of steps minus 1, we're going to compute the right-hand side, which is the number of nuclei divided by the half-lifetime, and with a minus sign, because of course the right-hand side is negative because we're dealing with a nuclear decay. The number of nuclei goes down in time. And so the number of nuclei at the new time step at i+1 is going to be given by the Euler step. So the current value of nuclei at time ti, the current derivative, the right-hand side, and the current delta t, that gives us the solution, the new time. And after we've computed that, we're going to also update the time by adding the time step to the current time. So this makes sense. This is the way to code the simplest Euler method of solving an ODE. So wouldn't it be better to try and nest this Euler step within a more general function that would take the steps one by one? That function will take an additional argument, the number of steps to take. So we don't have to worry about the details of what's going on under the hood. We basically say, can you please take 100 steps? And then we go have lunch, come back, and our method has taken those steps and has produced an answer. So we're going to call this function an Euler Solver, and we're going to give it an array x of solution, an array of times, and we're going to give it a constant time step and the number of steps to take. And so what this simple wrapper of the Euler step does, it loops over the steps, and it computes the right-hand side for the current value of the solution, and then it updates the solution at the next time step by taking the Euler step. And here what we've done is we've switched to the pointer notation as opposed to the array notation. However, as you notice, we still have this hard-coded derivative over here. It would be really nice to keep our method general so we are not stuck with solving for the radioactive decay forever. There are so many other interesting problems that we could use this method for. So for that, we would like to provide a function as an argument to our solver. This is pretty advanced stuff in C, but we're going to get through it. So we will create a pointer to a function that returns a type, some variable, and it accepts some fixed number of arguments. So this is the return type of the function, let's say integer or pointer or anything you want. This is the pointer to the function. And in this case, in this example, it takes 2 arguments and maybe more. You can specify however many arguments you would like. This is the type of argument 1, type of argument 2, and so on. So this is an example of such a pointer to a function sitting in function underscore pointer.c. And what we're doing here is we're defining the function add over here that takes 2 arguments, 2 integers, a and b, and it returns the sum of them. And the main function is also pretty simple. It defines 2 integers, x equals 1 and y equals 2. And then what it does, it defines a function pointer to a function that accepts 2 integers and returns an integer itself, which matches this definition. And it assigns this pointer to the address of this add function. And then it prints out the result of calling this function, just as we would call the function add itself, except here we write star f, dereferencing the function pointer, just like we would dereference a pointer to a variable. So we can use this new function pointer technique in order to create a more general solver where the time derivative dx dt would be a function of 2 variables, x and time, and perhaps some number of parameters like the half-life time of the nucleus. So let us see how we can implement that. We're going to define the function Euler Solver that accepts the array into which the solution will be placed, an array of times, and it also accepts the pointer to a function which gives the right-hand side of the ordinary differential equation, dx dt. That's a pointer because it's a star. It takes 2 arguments, x and t, and an array of parameters. And you can put a bunch of parameters over there. And these are the parameters that you can pass to the Euler Solver, and that Euler Solver will eventually pass them to this function. Plus, of course, just as before, we're going to pass the time step and the number of steps we would like the solver to take. So, as before, you probably recognize that, we're going to go in a loop over all the steps, and we're going to compute the value of the right-hand side by calling a function through the pointer that was passed to us, and we will give it the current value of x, the time step, and the parameters that were also passed to us. We're going to print out the resulting value of the right-hand side just to know that everything is working correctly. And then we're going to take the Euler step and assign it to the new value of x at the next time step. And we're going to do the same thing with time by adding delta t to the previous time. And of course, the right-hand side is declared, the right-hand side function is declared just as before, except now we're going to have the extra variable, which is the pointer to our parameters array. And I think that, yes, this is the closing parentheses and the brace. I was thinking I was missing it, but no, it's just hiding over here behind me. And just as before, in this function f, which is now separate from our solver, we are going to define the right-hand side, and we're going to return its value. And as you can see, the right-hand side doesn't use any global variables. It just uses a variable n and variable t that are passed to it. Plus, there are parameters which are not changing in the solution. These are constant parameters, such as the half-lifetime, for instance. And in this case, we're only using one parameter. But in more complicated situations, there could be more parameters passed through this array, and you could refer to them as parameters 0, parameters 1, and so on in the rectangular brackets. So this is how we would call the machinery that we just have created. We're going to define the maximum number of steps, and we're going to define the x and the t arrays. In our case, x is the concentration of the radioactive nuclei, and we're going to define a time step, which is reasonably smaller than the half-lifetime. And we're going to define the parameters, which is, coincidentally, is the half-lifetime, 1. So the time step is chosen to be much smaller than 1, but this is something that we would actually like to vary eventually to make sure that the time step is small enough for the error to be acceptable, small, at a level that is good enough for our purpose. So we're going to start with the initial conditions at time t equals 0, with the concentration equal to 100, and of course the initial time we will take to be equal to 0. And then we're going to call our Euler Solver, where we're going to give it the array of our solution with the initial conditions for n and t already filled in. So what the solver will do, it will start out with these initial conditions and take them out to later time. We're going to give it the parameters, in this case just a half-lifetime. We're going to give it we're giving it the address of our function, the right-hand side, which we defined on the previous slide. We're going to give it the constant parameters, a delta t, and the maximum number of time steps that we would like it to perform. And once we're done, we're going to print out the solution, values of n and time as for every time step, for every value of I. So the homework that's coming up, that will be homework 3, is going to ask you to do the same thing using Rangikatta of second and fourth order. Not only will you do that, you will also wrap up your solver into a library that we will call libod, that will contain not only these but also the Euler Solver. And then what you're going to do as well is compare the performance of Euler and Rangikatta solvers for the problem of nuclear decay.